Hello, this is our fourth in our series for the quantum physics section, the IB curriculum, and in this I'm not going to be spending too much time in it. We're going to be looking at the Schrödinger model and the Heisenberg's uncertainty principle. Now, it's really best for you, and I'd really encourage you in this to do some further reading and also to look at the multiple videos and so forth that you can find on YouTube and on the net, because it's not altogether so easy. We're not going to be going into the mathematics in great detail, but it is important that you spend some time looking at reading through your textbook and so forth. But with Schrödinger, and I've given brief definitions, and these come from your definitions sheets that you have. Now, what he looked at was that an electron could be viewed as wave functions, where the square of the amplitude of the wave function gives a probability of finding an electron at a particular point. So here we have electrons being viewed as waves, and the probability of finding them. So you will sometimes see those diagrams where you have maybe orbital shapes. Those give an idea of the highest probability of finding an electron. So they are viewed as wave functions. With the greater the amplitude of the wave, the higher the probability of finding it. Now, with Heisenberg's uncertainty principle, what he stated was that the position momentum or time energy cannot be precisely known. And he had two formulas, and we shall look at those briefly now. And you can see them here. Sorry about that. These are his two formulas here. These are the two formulas here. A bit of a few technical difficulties there. And here the X is for position and your P is for momentum. Now, the delta X is basically the accuracy where we can measure where a particular object is, like an electron or a proton. So the X is not actually a position, but the accuracy of that measurement. And here the delta P is also that, how accurately you can measure that value. So because it's greater than or equal to that, as the one gets bigger, the other will get smaller. I just like to use a simple example. If we've got X, Y is greater than or equal to 8, for instance, if X is equal to 1, then Y must be 8 or more, because 8 times 1 is equal to 8. If we had X is equal to, say, 0.5, then Y would have to at least be 16 to be equal to 8, let alone be greater. 0.1 for X, Y would have to be at least 80. So as the one gets smaller, the other one has to get bigger. And conversely, if we made Y smaller, X would become bigger. So what Heisenberg is saying is that as we get to know with more and more accuracy the position, then we have less knowledge about the momentum, the combination of mass velocity. And the more that we know about the mass velocity value, the momentum, then the less that we know about the x value. Now, this links up in some way to our view of with de Broglie's hypothesis, as it says over here. It says, for example, if a particle has a uniquely defined de Broglie wavelength, then its momentum is known precisely, but all knowledge of its position is lost. So we know that we have that the momentum is equal to h over lambda. So if we know what lambda is, in other words, if we have a single wavelength like that, we can say exactly or quite accurately what our momentum is. But if we make a combination or a whole combination of wavelengths in such a way that we have, and I'll draw this in green, in such a way that we have just like something like this happens, it's a bit funny there, isn't it? Where suddenly now we have more idea of the position, but then we would have much less idea of the wavelengths that make up that wave, which is together like a particle. And so here this would be much less accurate. So this gives you some idea of Heisenberg's uncertainty principle, Schrodinger's equation. Certainly they were very important in understanding quantum theory, building up a knowledge of quantum theory, and I'd really encourage you to do further reading on this whole aspect. Thank you very much.